So in this video, I want to take a look at writing a little assembly language program under CPM 22 on the Altair. And all this little assembly language program is going to do is you can type characters on this terminal and they'll show up down here, and you can type characters here and they'll show up here. It would be kind of a very early precursor to like a chat program where you could talk between two users. On my Altair, TTY0 is connected on COM5 on my PC, and TTY1 is connected down here. So let's jump in quick and just take a look at the assembly language program we're going to build. There's some defines at the top, or some equates. We're defining the 4 ports here that the SIO2 UARTs live on, so that's 10 through 13 hex. We've got the control port for UART1 and the data port for UART1. We've got the control port for UART2 and the data port for UART2 I mean. We've got the reset command in hex to reset the UART or the ACIA. We've got another command here that sets it to 8 bits, no parity, 1 stop. I've added an escape character. If I hit escape, it'll exit the little program. And then we have the vector to jump to if we want to warm boot CPM. And then the program is going to originate at address 0100 hex, which is where programs normally start under CPM. So we can look quick here at the assembly code. We're going to move into the A register, this reset command. We're going to output it to the SIO1 control port. And then we're going to output it to the SI2 control port, and that resets both the UARTs. Then we're going to pick up the byte that sets it to 8N1, and again output it on control port 1, control port 2, and then we go into a little loop here, and we basically look at the SIO1 control port to say, give me your status register. We rotate that right with carry, and then we jump with carry if there's a character waiting down to N1. If not, we check UART2, same thing, and we just loop here until there's a character ready to be read on one or the other of the UARTs. If there's a character waiting to be read from UART1, we jump down here and we do an in. On the data port, when this is the data, and we outport it to the SIO2 data port, we compare what was read right here, this read into the A register, with the exit character, the escape. And if the escape's been hit, we jump to their W boot vector. Otherwise, we come back up and loop again. And for N2, we do the same thing. Get the byte from the data 2 UART, write it out to the data 1 UART, compare it to an escape. If it's an escape, we warm boot the machine. Otherwise, we jump up to test 1. So this is all what the code really does. So let's start up the CPM machine. Power's on. Floppy drive is active. Let me do a reset. Examine address FF00, and my ROM is where the bootloader lives. And we see CPM start up at CPM 22. If we do a directory here of what's on disk, I don't know if I just typed dir someplace, and I sure did. Don't want that there. I've stripped down the normal CPM 22 image. Just leave a few things on here. It's kind of the standard stuff, but what we're interested in is really the, if I can find it here, the assembler. So this is the 8080 assembler from Digital Research, and this is the loader from Digital Research. And of course we have the line editor here, and I'm not going to try to type this code in the line editor. I'm going to cheat, and I'm going to copy it from this window in. So let's go ahead and do an ed to SIOPP is what I've named this, .assembly, and that'll open up the editor and should create a new file named 2SIOPP on the floppy, and it did. Lowercase I is an insert allowing lowercase. It's now in insert mode. We can copy this source out, and I'm going to paste it in here. A note here, if we look at the UART settings or the serial port settings, I've got a 25 millisecond delay between every character that it outputs, and a 100 millisecond delay after return is hit. And what those delays do is give ED here enough time to actually process the incoming characters. So let's go ahead and paste that program in, and we'll let it go here. And as far as CPM goes, I'm just an excellent typist and able to type this in real time here. Again, those delays were kind of needed so the editor could keep up on the machine. You know, this is a 1 megahertz 8080. It's not super fast. You know, if we wanted to be completely era correct, I would be editing this in the ED editor. Not a fan of line editors. I used them for a lot of years in the early 80s. I'm not going to go through the pain of that when I can kind of cheat here. So the code's been typed in. Control Z here in CPM is basically the end of file character. Control Z will tell it that we're through inputting. And then E will write the file out and exit ED. Hopefully you could hear the floppy drive accessing there behind us. Let's do a directory now and see what's on the CPM disk. And we find 2siopp.assembly. We're going to go ahead and assemble that with the ASM assembler, 2siopp.asm. And we'll let this, oh wonderful, why, that shouldn't have happened, BDOS error on M. I'm going to go ahead and do a warm reboot here, well actually a hard reboot, reset, examine. Since we did have a BDOS error, hopefully this disk hasn't gotten corrupted. And let's try that again, 2siopp.asm. I only have one drive on the machine, and that is drive A. And by golly, has this disk got corrupted? Ah, I know what I'm doing wrong. ASM 2SIOPP. I don't need the .asm extension. For the assembler, even though this is like a program extension, anything after this period are actually switches to the assembler, and that's the mistake I made here, was specifying the extension. I don't need to. It'll default to a .asm file. It's one of those little gotchas, and you saw it happen here, where for the digital research assembler you don't need to provide the ASM extension. It gets parsed as switches, you know, to the assembler. So now we should have another 2SIOPP file here, which is this hex one. Let's go ahead and type it out. Type 2SIOPP.hex. And what that is an Intel hex file. We've kind of looked at this before. It's got the load address of where it's going to start loading bytes, and then it's got the byte stream to be loaded at that address, and then a checksum out here for the line. And then it's going to move on to line, or to address 0110. Again, it's byte stream and a checksum. So this is a hex file that contains really the machine language code for what we just assembled. We've also got a PRN file here, and we go ahead and type it out to siopp.prn. And this has basically got the output from the assembler. And we've looked at stuff like this before. An address is 0100. We've got to move immediate to the A register, the value in SIO-RST. And in SIO-RST we have 3 hex, and there it is. We're going to move immediate to the A register this value. If we go back up and look at the hex file, there's the same 2 bytes. So at address 0100, we're going to load 3E and then a 03 into memory. There's the 3E03. So we've got a couple different files output here. So the next question becomes, how do we run this? The easiest way to get it converted to a COM file for execution is to do a load to SIOPP. And what load will do is load this Intel hex file and then convert it to a COM file and save it to disk. So we'll let this run, and it tells us, hey, we've done this. I loaded address 0100 hex. I go through 0132 hex. It was 33 bytes total. We should now have a COM file to siopp.com, which we can run from the command line. And this should be now running in the loop here where it's saying that we have a character waiting to be input from either port 1 or port 2, or UART 1 or UART 2. If I type a character here, there it is. It read the character from this terminal and wrote it to that terminal. I'm not typing into this terminal. I'm up here typing into this terminal. You can tell because the cursor is active here. If I bring this terminal active, we're going to be typing into this terminal. And so is this. And in this case, we're typing into this terminal and it's being echoed up in this terminal. So really, that's really the demonstration here. It does just exactly what we've coded here. It waits till there's a character waiting in the UART, it reads it and writes it at the other terminal. And that's, all this, little bit of code here does. The last thing it does is wait for an escape on either terminal. I'll hit escape here. And because of the escape, it's called the warm boot. It's jumped to that vector and the machine's warm booted back and we have the A prompt back. So really there it is. The steps were assemb to SIOPP. We'll just go ahead and assemble it again, just so we kind of get a clean demonstration here. Apologies for the sniffling if you can hear it. I've had a bad head cold for about a week. We then want to load to SIOPP. And that'll read that Intel hex file, convert it to a COM file. There it is. And we can run it again. And we're back where we were before. Can't type. I don't know what to type. test. I can hit Control Enter and send line feeds. And you can see because the cursor's flashing down here, I'm typing it down here and sending those up. You can come back up here and do a control insert and send line feeds to the lower terminal. And again, this would start to create the foundation for being able to chat between two different terminal sessions. Now, CPM isn't a multitasking operating system, so this makes no sense in this environment. Although, honestly, if you had two computers hooked together with serial ports, again, this could begin to be a foundation for that. Anyhow, I think that's really the end of the demonstration. This will be a short video, and we'll talk soon.